So E union E prime is contained within E. And that just means that E closure is in E. So, but E is clearly an E closure. So, since E is clearly an E closure, E equals E closure. Nice. And then in the reverse direction, suppose E does equal E closure. Well, then E contains all its limit points. Implies E contains all its limit points. Okay. Everybody happy with this? Each time you learn a new theorem, of course, you should sit back and ask yourself, does it intuitively make sense? And this one probably pretty easily does, right? You close something and it doesn't change, and it must have been closed to begin with. Here's a nice fact about closures. Suppose you have a set E that's contained in a closed set F. Well, then I claim that the closure of E, what do you think I can claim about the closure of E? It's also in F. Then E closure is contained in F. Oh, interesting. What this is saying is, in some sense, we know E closure is a closed set, yes? And any other closed set that contains E must contain the closure. So in some sense, the closure is the smallest closed set that contains E, right? So the moral of the story here is E closure is the smallest closed set containing E. Everybody see why this theorem is saying that? You can't, any other closed set must contain the closure. And the proof is actually pretty straightforward. Can anybody see what the proof is? F is a closed set, so F does what? Contains all its limit points. In particular, it contains the limit points of E. So it contains E closure as well. So, P, so here's another way to say it. P, if P is a limit point of E, P a limit point of E, would you agree that means that P is a limit point of F? But F contains all its limit points. So all the limit points of E are in F as well. F contains the limit points of E as well as E. And E. Done. Okay. Okay. Any questions about closures? So this is, so this is an important, some important facts to note. Okay, let's talk about the relationship between open and closed sets. What is the relationship? We have this rather curious definition for open, curious definition for closed. They don't really seem all that related, and yet I claim there's an intimate relationship between a set that's open sets and closed sets. So what's the relationship? What's the relationship? Let me prove a lemma that will perhaps help us see some things. Okay, well, actually, let me not prove lemma. Let me just state the theorem first that we want to show. So I claim that, in fact, if you have a set that's open in some metric space, X, E is open, I claim this is true if and only if the complement of E is closed. And I have to say what the complement is. So here, the E complement is the complement of E. And what that means is it's defined to be the set of all points that are not in E. So they're in the metric space X, but not in E. So the definition is E complement is basically X minus E, where X is the metric space that you're in. And if you don't like this set minus notation, which we defined a while ago, it's basically the set of all points in X such that P is not in E. So what we're saying in this picture is, if you look at everything outside the set E, that's a closed set. Would you believe that from this picture? Yeah, it sort of contains its boundary in some sense. Here, if you look at the set outside the square, it's in fact open. Another way to think about that is it true that if I'm outside this closed set, if I take a point, I can push it around a little and still be outside that closed set? Yes. So let's see if we can justify this this fact. So why is this theorem true? Okay. Well, let's prove it. Proof is not so bad. Suppose I start with an open set. I claim a set is open. Well, what's the definition of open? It means that any point of, let's call it X in E, is what? Is an interior point. All right, great. But what that means, this is equivalent to, means that for any neighborhood, for any X in E, there exists a neighborhood N such that, neighborhood of X, such that what's true about the neighborhood? It's contained entirely in E. Would you agree that's the same as saying, if this neighborhood's entirely in E, it means that N is disjoint from the complement. So the existing neighborhood of N of X such that N is disjoint from E complement. So I just turned this into a statement about E complement. So here's the picture. Here is an open set, E. Here is a point, X. And the claim is if X has a neighborhood around it that is completely within E, then this neighborhood completely misses E complement, which sits outside. Are you with me? All right, good. Now what? Help me. What's my goal? My goal is to show that E complement contains all its limit points. And I've just picked a point that's not in E complement. For any point not in E complement, it has a neighborhood that completely separates it from E complement.